In a previous video, I showed you a schematic for a series parallel circuit, and we worked out what the equivalent resistance for that circuit would be, and then we also worked out the total current, or basically the current coming out of the power supply. But now I've done a simulation of this, and I'm using what's called the circuit construction kit, the DC circuit construction kit from PHET, and I highly recommend you use this tool to help you understand parallel, series parallel circuits. There's a lot of other things you can do with it too, but right now we're using it to model our circuit that I used in the previous video. So one of the things we can do with this is I can hide the electron flow so you can't see the electrons flowing, and it looks just like a pictorial diagram for the circuit. I can also put it in schematic mode, and you can see what this would look like if you were using the symbols for resistors in the battery instead of what they actually look like in lifelike mode, which is what I've got it set for right now. So I'm going to unhide the electrons, and this is what the flow would look like. And some of the things you need to get out of this are what does it mean when a resistor value in a parallel combination is less than another value? Well, we can see that the electrons flowing, for instance, in the 4 ohm resistor versus the 6 ohm resistor in parallel, the electron flow is a little faster, which is what you'd expect. Not really so much faster, it's just the current is a little larger through the 4 ohm than it is the 6 ohm. Because you have this spacing between each of these circles pretty much represents a coulomb of electrons, and the spacing between them is wider, and you've got more of them going by per unit time than in the 6 ohm section. We're going to take some measurements around here just to verify that what we did as far as our calculations went, that our calculations were correct. So let's do this. And one of the things we want to notice here is that we've got the battery turned around so that the negative terminal of the battery is at the top and the positive terminal is at the bottom. And that's basically going to give you electron flow going upward. Electron flow is always going to be from the negative terminal of the battery and away from the negative terminal of the battery. When we talk about conventional current flow in electrical engineering, and that's really just a holdover from days when we believed that current was from positive to negative. It turns out it doesn't matter what your convention is as long as you're consistent with what you do. So when I go to measure a voltage across the 2 ohm resistor, for instance, I want to put the negative terminal here because that's going to be the negative side of the 2 ohm resistor, and this will be the positive side of the 2 ohm resistor. One way to think about this is that when we have electrons coming up through the circuit, on the negative side of the device, we're basically going to have what we can kind of think about as a higher electron density than we are on the other side of the device. And so when I do this, I get across the 2 ohm resistor, I get a 3 volt reading. Now, if I come over here I'm going to move the meter out of the way, and if I come over here to this parallel combination of 4 and 6 ohms, I get 3.6 volts. The current we calculated was actually 1.5 amps. We just took the equivalent resistance and we came up with 1.5 amps. So we can measure that here, 1.5. Now there's no reason for this current to be any different anywhere else. We can go anywhere in the circuit and measure 1.5. Now where we do have a problem is when it comes to a junction where there's 2 resistors in parallel. But what's going to happen is it's going to split up, and the sum of these currents, we got 0.9 there and we have 0.6 here, the sum should be 1.5. Obviously 1.5 amps of current can't split up in any way other than to create 2 currents that have a sum of 1.5 amps. So we have 0.6 and 0.9, and that's 1.5. If we look at other places in the circuit, like here, we get 0.75 and 0.75, which is a sum of 1.5. Here, the current converges back to 1.5 again. So anywhere we measure next to a series resistor, a single series resistor, we're going to measure the total current. And then we have it break up here into 0.75 and 0.75. And this is Kirchhoff's current law. The currents have to add to the total current. 1.5, 1.5, 0.9, 0.6 again, and 1.5 again going back into the battery. So measuring the currents, that's what we come up with. Now looking at the voltmeter, we got 3.6 volts here, and that'll be the same whether it's measured from here or here to here. Doesn't matter. If we come over to here, we're going to measure 4.5 volts, whether it's from here to here or here to here. We come across the 6 ohm resistor, and we have effectively 9 volts, 8.999. The simulator has some problems with rounding sometimes. Here we have 11.999 or 12 volts across this 8 ohm resistor. And down here we have 7.5 and 7.5 everywhere along here. Remember, the polarity on a conductor, anywhere in a circuit, if you follow a conductor, you're going to have the same voltage. There's no, in a perfect conductor, there would be no voltage drop. So that means that we're going to measure 0.7 anywhere along a conductor. Now when we hit a component, it's a different story, because going through that component there has to be a voltage drop. So up here we measure 19.5 because we're going across a component now. But for the wire itself, we shouldn't measure any difference. In fact, if I take the positive wire and go here, I should measure 0 everywhere along this conductor, because we assume we don't have any voltage drops across a conductor. In reality, conductors are 100,000 to 1,000,000 times more conductive than resistors, so it's such a large difference that we can effectively say there's no voltage drop across conductors, even though in reality there is a tiny voltage drop. It's just almost unmeasurable. Come across this component here, and we have 9 volts, and come across these two components here, and we have 5.4 volts. What we'll find is if we add all those voltage drops up, the voltage across the 2 ohm resistor, across these two resistors, across the 6 and the 6, the 6 ohm, the 8 ohm, all these resistors, this one, the 6 ohm, and the 6 and the 9 ohm, and those voltage drops ought to add up to 54 volts. That's what we call Kirchhoff's voltage law. Kirchhoff's voltage law basically says that the sum of the voltages in a loop, and this whole circuit is one loop, but the sum of those voltages has to equal 0. Another way of looking at the law is that the sum of the voltages in the load section of a circuit, in other words all the resistors, the sum of all those voltage drops has to add up to the supply voltage, which in this case is 54 volts. So this tool I recommend highly if you're going to work these problems. This is the tool to use to do it. It helps you visualize really well what's going on in the circuit. The limitations are that the largest resistance you can have is 100 ohms. But that's not such a problem, because you can scale things down. If you had, let's say, resistors that were 1,000 ohm resistors, or a 1K, a 2K, an 8K, a 6K, you can still simulate the circuit. It's just that you've got to make sure that you scale everything properly. So if my values were in K ohms instead of ohms, then I just have to remember that I'd still have the same voltage drops across everything, It's just that my currents would be 1,000 times less if everything was in K ohms instead of ohms. So this is a great tool. I recommend you use it, and every time I run a problem, I'm going to use the simulation tool to show you what's actually going on in the circuit whenever possible. So I hope you enjoyed the video. Let me know how what you think about this tool and how you did working the problem out.